right? So that will be Bm. X is equal to 0 theta by dx b times m. From this you can find, and b will know, minus theta b times m tan hyperbolic ml. Can you just observe that temperature gradient in case of finite length fin and infinite length fin difference? In case of finite length fin, this term was not there, only this term was there in finite length fin. And for finite length fin, this extra term is appearing, tan hyperbolic ml. If you see back, this, see here. Alright, so these things you should observe while deriving. So if we put a and b values in this equation, so we will have, after simplification, which you can try yourself, as theta is equal to theta b times cos hyperbolic ml minus mx divided by cos hyperbolic ml, or theta by theta b, which is nothing but t minus t infinity divided by tb minus t infinity equals to cos hyperbolic ml minus mx divided by cos hyperbolic ml. Alright, so now we have the temperature profile. So if we want to find that what is the temperature at the tip, what is the temperature at the tip, so at any x we can find the temperature from this equation. At x equal to L, T at L minus T infinity divided by TB minus T infinity equal to 1 by cos hyperbolic ml. Right. And then we should know the heat transfer from this fin will be minus KAC d theta by dx at x equal to 0. d theta by dx at equal to 0 we have already found from this. You can just plug in here. So we will get, after simplification, as KAC m theta b tan hyperbolic ml. And if we follow the similar procedure as we did in the case of infinite length fin, hp divided by KAC times theta b, we will have this expression hp KAC, h times parameter times thermal conductivity of the fin material times cross sectional area of the fin times base temperature, excess base temperature times tan hyperbolic EML, which is nothing but the fin heat transfer rate of heat transfer to the ambient. Okay. One more thing we can observe, that this thing collectively are the expression for the heat transfer from the infinite length fin. And for the case of finite length fin, this is the expression, means this term is extra is coming. Alright. So we can define a criteria that when we should say that fin, when we can treat the fin as of infinite length. So if we see for this ml, if this ml is 0, then hyperbolic is also 0. It means there is no heat transfer from the fin. If ml is like 2.65, this is defined in the literature, we can find that hyperbolic value of this 2.65 is 0.99, that is approximately 1, right? So this expression will boils down to HPKAC times theta b, alright, which is the expression for the infinite length fin. Okay, and if we further increase this ml value, the variation of this expression tan hyperbolic of 5 will not change too much. Okay, so fin heat transfer with ml, if we plot, it will go like this. Means after this 2.65, it will reach to this heat transfer from the infinite length fin expression. Alright, so when we should treat the fin as of infinite length. So this, in actual practice, when ml is greater than 2.65, the fin is treated as infinite length. It is infinite length fin. And because I running calculation between the considering the fin as finite and infinite is very less. Okay, so error is less than actually 1% by considering the fin as infinite or finite, right? So one more case in this finite length fin is that if we relax the assumption of this adiabatic tip, that is, if we consider the heat transfer from the tip also. So case 2b, if we see, then let's say this is our fin, at base temperature Tb, at temperature TL, at x equal to L, and apart from lateral side, it is also convecting heat from the tip as convection. And from here, convection temperature profile. Outside this, we have fluid, so fluid temperature variation. It is not. This is fin temperature variation. This is fluid temperature variation. because fluid in contact with the tip will be having high temperature as compared to the fluid in ambient, right? And this will be having like this ambient fluid temperature at some distance away from the fin. All right. Fin temperature variation. There will be discontinuity here. All right. So what is happening at the tip? If we look carefully, what is happening at the tip? Actually, fin tip, if we consider a control volume around the tip, on one side it is receiving the heat from the conduction from the adjacent volume, and on the other side it is releasing heat to the ambient adjacent volume on the right hand side. Right. So this will be the boundary condition for this case. All right. So this is also called the Robin. This should balance, right? They should be equal to each other. K d theta by dx. We can also write like that because AC will be cancelled on both sides. So H times theta or theta L, which is nothing but H times TL minus T infinity, which is also called Robin boundary condition. All right. So if we follow the rigorous approach, we can find the temperature variation and the heat transfer for this case. Rigorous approach, which is the same as we did for the above cases. So the expressions will come like this for temperature variation, theta by theta b. You can take it as exercise as cos h cos hyperbolic ml minus mx plus h by mk sine of hyperbolic ml minus mx divided by cos h ml plus h by mk sine hyperbolic ml. And for the heat transfer,